So let's get into solving, finding specific solutions. This is 4.1b. Find specific answers to integration. Finding specific answers, or what do they call them? They call them, I think, particular solutions. Yeah. AKA particular solutions. Particular solutions. We're going to look for a particular solution to an integral. Remember, we have this normally when you do an indefinite integral. Your answer has this plus c, right? Recall. When you integrate, you add this plus c. And the reason why was because if I do, like, for example, if f prime, if my derivative was equal to, let's say it was 2x, right? My original equation, f of x, could have been x squared. Or it could have been x squared plus 2. Or it could have been x squared, or it could have been x squared minus 5, right? Or there's an infinite number of possibilities what my original equation could have looked like. Infinite possibilities. Possibilities. There's only one S? There's only one S. Infinite possibilities. So we say f of x equals x squared plus c. Is the screen frozen for anyone else? Okay. There. Got it. I was on the wrong setting. My apologies, everybody. There we go. That better? All right. Sorry, everyone. Sorry, everyone. Here's what I was writing. You couldn't read. All right. So notes 4.1b, finding specific answers to integrals, which is aka a particular solution. We call these particular solutions. Oops. Particular solutions. And what I was talking about here, right, when you have an integral, you add this plus c, because if you have an answer, if you know what your derivative is, you don't know which one of these was your possible original equation, right? Oops, you're still writing. So that's why we add the plus c, right? Because we don't know which of these could be minus 5, could be plus 2, could be anything. Right? So we say plus c to kind of cover all the possibilities. We say plus c. And if you can imagine what this looks like visually, right? Visually, if I have the graph of the derivative f prime, looks like this, right? Looks like this through the middle, like this, right? This is 2x. Right? That's what the graph of 2x looks like. f, we said it was x squared, right? Well, f could look like lots of things. Could look like this, right? This is x squared. Could look like this. This is x squared minus 5. Right down here is minus 5. Could be this one, x squared plus 3. Right? Here's 3. So all of these, and an infinite number of them, right? We could go plus 1, plus 2, plus 3, plus 4, plus 1.1, plus 1.2. Plus, there's an infinite number of possibilities. I could have this graph in all of these different places. So if we're looking at a graph, this is what the possible graphs look like, right? And this equation going down here, down to negative 5. This equation going up here to positive 3. 1, 2, 3, 1, 2, 3, 4, 5, right? You can have all these different, like, parabolic, quadratic graphs in all these different locations. And all of these, every single one of these, has the exact same derivative. They all have the derivative of 2x. Because the constant part doesn't matter. Because they all have the same slopes, right? The slope here is the same as the slope here. Right? Here is the same as the slope here, is the same as the slope here. They all have the same slopes. It doesn't matter where they are, right? Remember, we're looking for the change of the equation. We don't care if it's, it's relative to other parts of the equation. We don't care really where we put the equation. The equation can be lots of different places. It's just about the slopes. All their slopes are the same in each same location. So the derivative is the same for all of them. Because the constant part doesn't matter. Which is a very interesting thing about integration. Right? Very interesting thing about derivatives, right? We just care, it's like relative positioning. We only care about the relative position of the graph itself, not where it is in the axis. It's just about the equation and the curvature of the graph. So they all have the same slopes, so they all have the same derivative. Really interesting. But what if we want? How can we find figure out which graph, which equation is the right one, is the specific solution, is the correct particular solution. How do we figure out which one we want? I guess maybe let me say how to figure out which, not that. Let me say which equation or which one we want, which graph we want, which one we want. Which of these equations, which of these graphs is our particular solution? Which of these potential equations is the one that we really want? Which one is the actual original equation for our particular derivative? How do we know? How can we figure it out? Well, to figure it out, you need a point. You need a value. You need a initial value. Initial value of the original function. Original function. to figure out which one of these possible graphs is your actual solution, you're going to need a particular solution. Is this part of your answer? Or is this part of your answer? Or was it this point here? Which of these points, right? Which of these values is the value that exists in your original equation? It's an initial condition point. Like it's a solid starting location, and from that starting location, you can then figure out, oh, they wanted this equation. They wanted, if this is my point, the only original equation that goes through that point is this one. We need an initial value to figure out which particular graph, which particular equation is the one for us. We need this particular solution. And so we give this initial function, right? We say it's f of, what do they call it? I use whatever letters, f of k, hold on. Well, anyways, it's an initial function, initial values, initial value. F of x, we need it to equal some number. We need some initial value equation, right? F of a equals some particular number, right? We need some input. It gives us an answer. So let me give you an example. Find a particular solution. Find a particular solution for, let's do this one here. If f prime of x equals 3x. And I'm going to say that if f of x, I'm going to give you a particular solution here. F of 1, hold on. F of 1 equals 2. So this is my initial condition. Initial condition. And so what we're going to do, the steps we're going to do, is we're going to integrate to get the equation, to get the plus c, and then we're going to plug in x and y to find the c value. Right, this is my x value, this is my x value, this is my y value. Plug in the equation in x and y to find the particular c. So we integrate first, we do our integral to get our general equation, and then we plug in the initial condition to find the specific equation. Which c are we getting? What's our c here? So I want to do the integral of 3x dx. And what's that going to equal, everybody? Integral of 3x dx. Integral of 3x. Well, let's follow my power rule. The integral of 3x, that's going to be, well, the 3 stays in front. Right, that 3 is a constant, it just pops out. 3 is still there. X, I use my power rule. I bring the x, I'm bringing an x back in. So I'm going to make this x squared. I'm adding 1 to the x. And then since I added 1 to the 2 here, I have to divide by 2 as well, plus c. Okay? So there's my equation. There's my integral, right? There's my general integral. It's 3x squared over 2 plus c. So that's the general equation. Right? My general, indefinite integral. If I want to find a specific answer, though, I know this initial condition now. I know that if I plug in a 1, if I plug a 1 into this equation, the answer to that equation is going to be a 2. That is what my initial condition tells me. That if I plug a 1 into this original equation, because this is f of x. This is f of x, right? This equation here. So I know that if I plug that's this equation here. This f of x is this thing here. So if I plug a 1 in to this equation, I'm going to get a 2. So I can use that information to say, okay, well, I know that if I say 3 times 1 squared over 2 plus c, I know that's going to equal 2. And now I can solve for c. Let's see. 1 squared is 1. 3 times 1 squared is 1. 1 divided by, that's going to be 3 over 2, plus c equals 2. If I subtract from both sides, minus 3 over 2, minus 3 over 2, that means that c is going to equal, let's see, 2 is 4 over 2, minus, that's going to be c is 1/2. And c is 1/2. So that means that my specific solution is f of x equals 3x squared over 2 plus 1/2. This c value gets plugged back into there. Oh, goodness gracious. This c value gets plugged in back to there, and I have my particular solution. I found a particular c that helps me get a specific answer to this equation. What specific equation am I looking for that has this initial condition? So that's going to be what I'd like you to try this evening. Okay, we got like 2 minutes. You can do this more than once as well. What if I said, another example, just quickly, if I said f double prime of x was equal to, let's see, 6x, and I said f prime of 2 equals 1 and f of 2 equals 0, find f of x. Well, now I have a second derivative, so I got to do what I just showed you up here. We have to do this twice. I do it once to find f prime, and here's my initial condition for f prime, right? So 1, find f prime. 2, use that f prime to find my f. So I have to do the process twice. I integrate here, and I plug in. And then I do it again. I integrate, and I plug in. So I'm going to get an integral. I'm going to find a value. I plug the value in. I get a c. I use that real equation. Now I find that real the particular solution to f prime, I integrate that one, and then I plug in again my initial condition for f, so I just do it twice. So that's how we can do this kind of problem here. If I did the integral of 6x, that would be, let's see, 6x squared over 2 plus c, so that's going to be 3x squared plus c. If I plug in my initial condition, this is f prime here. So this is f prime now. So I'm using my initial condition here. I'm plugging in a 2 and equaling a 1. So 3 times 2 squared plus c is going to equal a 1. That would be, let's see, 3 times 4 plus c is 1. That's going to be 12 plus c is 1. That means c is negative 11. So this f equation, f of x, f prime, is 3x squared minus 11. And then I do the integral of that. 3x squared minus 11. That's going to be 3x cubed over 3 minus 11x plus c. So x cubed minus 11x plus c. Now I plug in 2 and get a 0 into this one. Plug in my 2, get a 0, right? This is my this is f here. So I'm going to get 0, oh no, sorry, 2 squared, 2 cubed rather, 2 cubed minus 3 minus 11 times 2 plus c equals 0, and solve that one. Eight minus 22 plus c equals 0. That means that c is, let's see, 8, 16. So f would be x cubed minus 11x plus 16. And there's your answer. So again, you just do the process twice, plug in the one initial condition, get the first c, take that equation, integrate it again, get another c, plug in the second time, and get your other c. All right, your homework is up on Schoology. We're going to go over this on Thursday. I will see you all tomorrow at our little study session for the AP test. Come tomorrow. If you would like, we can do more of this tomorrow. Review this instead of our AP test. We could do the AP test maybe Friday. I don't know. I'll take a poll. See how it works. But that's it for us today, everyone. In the chat, type goodbye. I'll post this up on Schoology. Thank you very much, everyone. Short class, but I'll see you all next time.